Perfect. All right. Hello, everyone. Welcome to Barcelona. If you're just coming here, I hope you're enjoying it. I'm Peter. I'm from the Barcelona Supercomputing Center. And to follow up on the quantum talk we just heard, I'm going to discuss a potential future use case for hybrid quantum-capable programs in the context of HPC. OK, so what you're looking at here is Alia. It's a computational physics simulator. And it's developed at BSC. It was developed for supercomputers from the ground up. So it's a highly efficient parallel piece of software. And the scaling properties are also very favorable. So you can add or remove resources as you want, and you can be fairly sure that that's going to scale in a predictable way. I said it's developed for parallel systems. That also means it's able to use all the different levels of parallelism that we have in our HPC systems. And it's even able to, maybe integrating with another piece of software we have, DLV at VSC, adjust the resources it's using internally to make sure the simulation as a whole is balanced. But one thing that it can't do is adjust the whole of the simulation in terms of how many resources it's using. And this is a common HPC problem you'll be aware of. You allocate 5 nodes in Slurm, for instance, and then you're stuck with those 5 nodes until you relaunch the entire application. And this is what we try to tackle with DMR, which is the library that I'm involved with working on. I'll introduce it a little bit more later, but the important part is that we can integrate into pieces of software like Alia to enable it to add or remove resources while it's running. And we take into consideration usually how the simulation is doing, so how efficient is the application currently. We could also factor in how the cluster is doing as a whole. Do we have resources to grow into, or are we stretching our limits? And we could use any arbitrary metric to make decisions. And for Alia, it might look something like this. So imagine we're targeting this shaded gray area. You have the dashed red line being MPI processes, and the blue line representing communication efficiency, which don't worry so much about it. It's just a metric of how much time is being wasted in your MPI application by communication. So you can see we start off with a very high communication efficiency, maybe too high, because it implies that we could add more resources without sacrificing too much efficiency. And so we add stepwise resources until we sort of overshoot and have to correct a little bit, and then we end up in this gray shaded area. And the important thing to note here is that this process is entirely dynamic and can be identified at runtime. So if you have a simulation that has varying degrees of resource needs, our malleability framework would be able to accommodate that need easily. But backing up a little bit, so yeah, we just had to talk about quantum computing. And one thing that was mentioned was that a potential future use case for quantum computers are that they might serve more like accelerators to existing HPC infrastructure. So what I mean by that is that maybe not every single algorithm that you run is suitable to a quantum computer and would be more properly used in a classical system, and vice versa. You might have some part of the algorithm of your application that's more suited to a quantum computer. So there could be this sort of interplay between the two systems where you give some data to the quantum part, get some data back after processing it, and so on. And an application that works like this could look like this flowchart here. So we're iterating round and round in a circle. We have some main conditions, such as how accurate is our solution compared to how we want it to be, and then are we exceeding some maximum threshold iterations. And then we have these two distinct stages. One classical stage, the classical algorithm, and then the quantum stage. And the only thing you need to note here is that in this case, at least, the stages depend on each other, but they are not able to run in parallel. So you do the classical stage, you're not using the quantum resources. And you do the quantum stage, you are not using the classical resources. OK, so how might this look like in our traditional resource management environment? So on top here, I'm going to show you quantum resources. Not really important what the exact unit is. It's just for illustration that we're using quantum resources at that point. On the y-axis, you have time. Same y-axis on the bottom, but there we're showing you the classical resources. So it would be something like nodes in Slurm. So say you have two jobs that are submitted, job 1 and job 2. Job 2 is submitted slightly after job 1. And you can imagine these are hybrid applications following something like the flowchart that I just showed you. Now, in a classical, traditional resource management environment, job 1 gets allocated first by Slurm. Say you reserved 3 nodes. You only have 4 nodes in your cluster. Now you have this block and then this idle part that's currently not used. And then your application enters the quantum stage. And you'll recall I said you don't actually need the classical resources while you're in this quantum stage. So in just a normal execution here, we have this dark blue area where we have allocated resources to job 1, but we are not using them. And now, say the application continues to run for a while, and goes out of the quantum stage, then we could finally, at the point where job 1 completes, finally get job 2 out of the queue and start running it. And you can imagine this is not the ideal way to do things. So the obvious question is, can we do better? And with our malleability framework, yes, we can. So this would be the ideal way to do it in a malleable way. So you can see that from the start, instead of waiting all the way until job 1 is complete, we allow job 2 to launch with a suboptimal amount of nodes. So say we only let it run with 1 node from the get-go. So instead of queuing, it can at least do some amount of work. And then when job 1 enters its quantum stage, it can say, hey, I don't need as many nodes anymore, so I'm just going to drop them. And conversely, job 2 can then notice that this gap has appeared and fill it. And the same thing then happens for job 2 when it enters its quantum stage, drops the resources, job 1 fills them up. And then finally, job 1 completes. And in this theoretical scenario, job 2 is then allowed to fully use all the resources that we have in the classical part. And you can already see that this use of resources is a lot more efficient. And I mentioned DMR earlier. This type of malleability is enabled by our library called the Dynamic Management of Resources Library. And what our aim with DMR is really to make your MPI-based application malleable in the simplest way that we possibly can. And this little chart here shows you how it works conceptually. You start with your first communicator, MPI-com world 1. You have a data set, say the data items 1 through 8. They're divided between the two processes equally. So P1 holds 1, 2, 3, 4. P2 holds 5, 6, 7, 8. Say then that you want to expand your world, add more processes. No problem. We're doubling it in size here. So adding 2 processes, making a world of 4 processes. The data set stays the same, but it's now distributed throughout the processes differently. And finally, as might be relevant here, you might want to minimize or drop as many resources as you can without terminating the execution completely. You can do that, and you would end up with the whole data set owned by the one process. So that's the conceptual view of how it works. If you're interested in the technical details behind it, I have it here. So we're relying on a feature in MPI called MPI-com spawn. And MPI-com-spawn allows you to create a new communicator and launch a executable and connect the two communicators. So in this example here, you start with two processes holding some data set here globally, these two pieces of data in green and blue. And these would then call MPI-com-spawn to create a new communicator. And the new communicator is actually the entire size that we're aiming for after we're done reconfiguring. So instead of just adding two processes, we actually add 4 processes to our execution. But you'll notice we still have the data in the wrong place, so we need to do something to process the data and make sure it's laid out in the way that we want it to be. And this might actually be the most technical part of using the library, because every application is different, and we can't really tell you how you should redistribute your data. Once you have it prepared, you just transfer it through maybe MPI mechanisms, or we're very flexible. You could use something like checkpoint restart, and you make sure it ends up in the new communicator that you just spawned. And when you're done, there's no need for the original communicator, and you end up with the expanded world, and it looks like your communicator just grew. And the resource stack that we have for DMR looks a little bit like this. We rely on some kind of parallel runtime. MPI is the obvious dependency, since we use MPI-com-spawn. We've mostly been using OpenMPI 5.0.x, but we are not bound to using that either, as long as the features that we need are supported. Some type of resource manager is also needed. On Mare Nostrum 5, which is the supercomputer here in Barcelona, we run Slurm, so that's the obvious contender for what we're going to run with. But we are also looking into future collaborations and branching out to other resource managers, maybe Flux, who knows. And we also need some type of way to decide when we should reconfigure. And for this, the classical way that we've done it is to use a performance monitor. And TALP is one that we've used. So in the graph I showed you earlier for Alia, the metric we were optimizing for was communication efficiency. And that's one of the metrics that you can get from TALP, which is part of the DLB library developed at BSc as well. But again, this is arbitrary and very flexible. We could use any metric that we want. We just need some way to make these decisions. OK, so on to the actual experiments that we've done for this. With DMR, we usually reserve one node just to manage the Slurm allocation. This is just done for technical reasons, but it's shown in this chart here. And we were running for this proof of concept just with 3 classical nodes, and then one quote-unquote quantum node. And I'll note this is not a real quantum node, but the more important part for us for running these experiments was that it simulated the behavior of how long it would take to offload onto a quantum system. So our hope is that in the future, we can actually run some real offloading to real quantum systems. But for now, this works as just demonstrating the concept. And if you recall the flow chart, we launched an application similar to this as a job to Slurm. And then we experimented with a long quantum offload stage that's on the order of a few minutes, and then also one that's short, on the order of a few seconds. And we did a single instance execution and 2 concurrent instances. So we're only working with 3 nodes in total here, so we couldn't really launch more than that without it not making sense anymore. And the application with DMR included looks a little bit like this. So if you'll skip to line 4, you have this while loop. So with DMR, we prefer applications that are iterative like this, because we like it when you have recurring points where you can check how your application's doing and when to make reconfiguration decisions. In this application, comparing to Alia, where we're optimizing for the metric of communication efficiency, in here we are expanding and minimizing based on the state of the application. So right as we enter the loop, if we reach that first stage, that means that we want more resources. And that's what this pseudocode DMR expand is telling you. So that is to say, we want to acquire as many resources as we can, up to some maximum. And then if we are able to do that, then we need to somehow take our state and transfer it on to the next communicator, because we'll be spawning one in the way that I just showed you. Then we just do our classical stage. And the opposite is true. After the classical stage, we want to drop as many resources as we can without terminating the application. And most of the time, it's trivial to drop resources, to queue for anything. But we could also imagine a scenario where we fail to expand and we're currently running at the minimum number of resources, and then there'd be no point in trying to reconfigure. We do our quantum part, and the loop goes on like this until we're happy with the solution. So again, this quantum part, the important thing to note is it's just a simulated time that it takes to return some solution, and it gives us something that we can keep on working with in our application. And that takes us back to lines 1 and 2. If this is not the first time we launch the application, then we somehow need to retrieve the state as it were before we started reconfiguring. And the metrics that we'd be interested in here are primarily total resource usage. That is just this shaded red area in the toy graph I'm showing you. You could have many jobs, so it'd be the sum of all shaded areas. And then the make span is also something you might be interested in. That is just the ending time of the last job minus the starting time of the first. And as I said, we're only really going to consider the classical part here, because the applications we're launching are going to behave identically in terms of the quantum part. And DMR is obviously a piece of software for classical systems. So here's what it looks like when we launch a static execution. So this is without the DMR library and without any tricks to let go of resources. So here we're running with a long quantum stage on the order of a few minutes, and 2 jobs, just the way that I showed you in the example graph. And even though there are multiple quantum stages in this graph, you cannot see them, which makes sense because we cannot ever relinquish resources once we're running our jobs. And the entire execution of these 2 jobs back-to-back takes around 2,000 seconds. The first one is done after a little bit more than 1,000 seconds. But if we run with a single malleable instance, we immediately start to see the fact that we have a quantum stage. So if you pay close attention to the graph, you can actually see that job 1 here launches with a single node. It then reaches this point in the code where we're trying to expand. And since the cluster is empty, there is plenty of room to expand. So we restart the application with 3 nodes. Then we run until we hit this point where we're about to do the quantum offload stage, and immediately let go of all our resources until the stage where we hit the classical stage again. And it makes these little neat gaps in the chart. And when we're running with 2 malleable instances at once, it might look something like this. So in this case, I'm actually showing you the short quantum stage. And the same sort of neatness with the gaps in the graph can be observed, but if you're able to spot it, you can notice there is somewhat of an issue here, which is that in this execution, what ends up happening is when job 1 gives up its resources, it's never able to reacquire them. This is not really an inherent flaw of the approach, but more of a demonstration of a trade-off that you might need to consider when you use our library. That is to say, you need to check for these gaps recurringly, but in your application, it might not always make sense to check for opportunities to expand. So if you do it too often, maybe that drains your resources. And you might also just be in a state in your application where saving it all down and transferring it back would be impractical. So yes, there is a resource a benefit for resources here, but it's not maybe the ideal thing that we'd like to see with DMR. But if we instead run the same type of experiment with 2 malleable instances, we start to see that these both applications are working in the way that we'd expect them to. So job 1 launches, 1 node immediately sees that the cluster is empty and is able to expand onto all the resources. Once the first job enters its quantum stage, it drops back to 1 resource that is just checking for the completion of the quantum part. And that's when job 1 is scheduled, or launches actually with a single node, checks if the cluster has any empty space. It does, and expands to 2 nodes. Then you will see these recurring gaps in the graph. These are actually just the points where neither of the jobs requested any resources. They are both in the quantum stage. So it wouldn't make sense for either of them to hold that resource. And yeah, this is how we'd ideally like to see it. With the long quantum offload stage, there's simply more of an opportunity for both of the jobs to enter a state where they're checking if they can expand or not. And that's not to say that the first approach can't be addressed. It's just a cautionary tale about the importance of application design. So I hope I've convinced you that the dynamic approach, so our DMR library, is an efficient way to reduce both the make span, that is the end time of the last job, minus the start time of the first, and the resource usage of your jobs. That's the shaded area. And I think comparing this to the Alia use case, you can tell that our library is very versatile, and we can really tune it to any potential metric. And I will say that even though quantum computing is a flashy thing here, we could replace it with almost anything you could think of. For instance, GPUs, or any application that would have a non-uniform resource need. And yeah, we're always looking for collaborations, so if you're interested, reach out to me. Maybe your application would benefit from our malleability framework. Here's my team, accelerators and communications for HPC. Antonio Peña is my group manager, and my mentor, Sergio Isert. If you're interested, we have a hackathon coming up at VSC. It's actually sponsored by Do It Now, so the QR code here will lead you to that, or just type in MNHack25 into your search engine. And what I just said about collaborating with DMR, that is one thing you can absolutely do. If you sign up for the hackathon, we can help you integrate your application into DMR and see how it works. Especially on Mare Nostrum, it's ideal because that's what we developed it for originally. Thank you.
Thank you so much. Do you have any questions?
Do you have other use cases rather than Alia that are using DMR? And if so, have you ever tried an earth science system code?
What was the last part, sorry?
If you tried with an earth science system code, a weather code, a climate code, or similar?
So there is one big one we're working on. It's to do with flood simulations. So they have this resource usage pattern that's very, very non-uniform, where you might have flash floods that, if you're simulating them, create a huge demand in compute over a short amount of time, and then reduces to almost nothing. So that is one use case we're working on right now for DMR.
DMR Leap, it's a new thing for me. So the closest thing I have seen is Charm++. That's kind of quite an ancient currently. So have you considered using this? So the use case, it's beautiful. It's pretty well explained, but like another degree of backfilling. So backfilling is used for filling up gaps in a cluster, but having the ability to grow and shrink based on how much resources you have available in the cluster and filling up all those gaps on demand dynamically looks like a pretty good use case as well. So have you considered, or your group have considered something like this as well?
Yeah. So there's sort of two aspects to it. Like from the one point of view, we could develop something that helps your application's needs. And this might, like, from a technical standpoint, be easier to achieve because we don't need knowledge of the status of the cluster to do it. But one other field of research that we're doing is being aware of how busy is the cluster, how we using resources, and then being able to just grant certain jobs more resources, not based on whether or not they're overperforming, but based on whether or not, or they'd have some preference. They'd always like to have 8 nodes, but maybe they're fine running with 4. And then we can sometimes grant that preference, and other times we'd say we need to look out for the cluster now. Yeah.
Awesome. Yep.
Maybe, I don't know, we have a classical case of having a program that is serial during one time, and then it's parallel, and then it's going back to serial, and maybe you can use this for optimize the use of the cluster. I was thinking of that.
Yeah, this is absolutely, like, for the same reason that this works, that would be an excellent use case for DMR, and something that'd be hard to achieve with current, like, Slurm technology.
More questions?
So, thank you for your presentation. I thought it was really interesting. One of the things that we've seen a lot of requests from users for, like on the side of trying to build a new resource manager, is more support for data stage in and stage out. And so I'm just curious in your library how you how you synchronize or know when the quantum processes are ready and the data is written, and like just to scale up or scale down. What was your approach to trying to synchronize that, status?
Yeah, no, in this case, it's just application dependent. So I wasn't fully involved in writing this part, but there is some kind of scheduler that they have for a quantum simulator, the team that we collaborated with. That will just, I think it just wrote a file to disk to indicate that it's done. And then we have the one process that's left alive, just kind of busy waiting for that file to appear. So nothing super advanced, unfortunately.
Something that I didn't fully got is when you change the com world and you change the number, is the user that needs to manage the redistribution, all that the memory is per process to redistribute to this new decomposition?
Are you asking if that's like something that the user has to do?
Yes.
Yeah. So the user unfortunately has to take care of that because every application is different.
So it's different per application, so it needs a custom development.
Yeah. One thing that we have been not experimenting with, but thinking about is can we provide a helpful toolbox for standard use cases? But to have a one-size-fits-all solution, I think it's not happening anytime soon.
Okay, so thank you so much.